Okay.
So it's recording. Okay. Uh, Today we will be overviewing the HyperSpecNet11k datasets, which is a large-scale hyperspectral dataset from uh, sorry. I'll start again. Okay. Uh, Today we will be overviewing the HyperSpec dataset, which is a which is constructed by the Remote Sensing Image Analysis (RSIM) group at TU Berlin and the Big Data Analytics in Earth Observation Group at the Berlin Institute for Foundation of Learning and Data. This HySpec Net11k is a large scale hyperspectral benchmark dataset made up of 11,483 non-overlapping image patches acquired by the ENMAP satellite. In this, each patch is a portion of 128 cross 128 pixels and 224 spectral bands and with a group sample distance of 30 meter. So moving ahead, uh, for the reference of this dataset, you can get it from the Git repository over here, and the research paper corresponding to this can be accessed from this link, and the dataset link can be accessed from here. In this, we have uh, we have 5 different models in which we have 1D CAE, then we have a advanced 1D CAE, then we have extension of 1D CAE, then we have spectral signal compression network, that is SSCNET, and in the last we have 3D conventional autoencoder 3D CAE model. All these models can be accessed from the link from here, and in this we have used SSCNet compression network model, and I can give let's go for the like little bit overview of 1D CAE. Like it is designed for the hyperspectral data compression using 1D convolution. In this, encoder reduces the spectral dimensions with successive convolution and max pooling layer, and decoder mirrors the encoder with upsampling and transposed convolution to construct the data. This is basically suitable for loosey compression and spectral data. And then we move ahead with the 1D CAE advanced. In this version, the CAE1D with changes in pooling. In this, we have used average pooling and two-step in decoder. In this, introduces transposed convolution in the decoder for better reconstruction. And for the extended 1D convolutional autoencoder, we have it has with adjustable compression rates using varying number of encoder-decoder block, employs batch normalizations and allow dynamic adjustment for different bitrate. For the modified 1D convolution autoencoder, we have multiple bitrate by varying encoder and decoder configuration. And it uses leaky ReLU activation and hierarchical encoding for spectral compression. For the 3D convolution encoder, we have both spectral and spatial redundancies with 3D convolutional layer. It includes residual blocks in encoder and decoder for improved feature extraction and reconstruction. And In the SSCnet, we have it is fully convolutional 2D architecture for spectral compression. This optimizes for high compression ratio by reducing both spectral and spatial dimensions simultaneously, and it includes latent layer with adjustable dimension to target specific bitrate. Now, going ahead with the first of all with the environment setup, you will need Python 3.10 and upper version for this. Then you need NVIDIA GPU with CUDA for computational purpose, and Ubuntu is recommended in this one. All the dependency files can be accessed from here, which is in present in the Git repository, which was mentioned over here. And for the data preparation, we have you can download the data from the link over here. And in this, we need to pre-process the num and py file, the pre-proposed hypertextual data for each patch is stored in numpy format, which is data.npy. To generate this, the pre-processed numpy files, we have to run the tif2npy.ipynb notebook from the HySpec tool, which is present, which can be accessed from this link and also present in the repository. In this, basically what we are doing are that the original band is 224 spectral band, which are getting reduced to 202 band, in which basically band 127 to 141 and band 161 to 167 are removed due to strong water vapor and absorption effect, because we do not want those things to be account in our calculation. Then if you go further ahead for data set overview, then the data set is look like something like this. Like you will have one root directory, which is named as HySpec11k, and in that you have the patches directly in the patches. And in each patches you will have tile directory, which will name as tile underscore 001. And in each tile you will have different patches for each tile. So if I talk about, then there are in patches we have 25 tiles, and in each tile we have different patches which may range between 45 to 52. So if we talk about the main file from one patch, then we will have these things in that we will have the TIF for the different entities like land, cloud, snow, etc. And now we are going for the splitting of the
I
data
think
set.
I think you should little bit explain about those different files, because people don't understand what those are needed.
Okay. So if you talk about the files, so we can see here, like in this, like we have different files. So in this we have two files, which is we will start with the like VNIR file, which is visual and near infrared files. This is approximately ranges between 400 to 1000 nanometer, covering the visual spectrum and slightly beyond into the near infrared. This is this file which you can see over here. You will have this one, these two files. So these are used for like utilizing chlorophyll observation for like vegetation monitoring and water body analysis. And the other file, which is SWIR, which is short wave infrared, which ranges between 1000 to 2500 nanometer, which is sensitive to moisture and content and mineral composition. These are also used for the like mineral mapping, vegetation stress analysis, and fire detection. Now, if we go ahead with the data splits. Then in this we have splitted the all the data into three different categories, like training set, which is the seven, which covers the 70% of the patches, then validation set, which covers 20% of the patches, and test set, which covers 10% of the patches, which is further split into easy split and hard split. And if I talk about the directory, then it looks like something like this. In this we have the like main root. In this we have the data set and then patches. Then in patches we have the tiles, and in tiles we have the all the files over here.
Uh,
And in that
I
you
think
have
I think it's better to explain about the other uh, cloud and the cloud shadow and snow, those files. You didn't mention anything about those files.
okay. If you go ahead about the cloud shadow or cloud, then these are the things which basically we have in images. We have different kinds. So like these files are present. Like for the cloud, we have different bandwidth to detect it, and even with to detect the cloud shadow, we have different band to get that one. So these are the files which basically have different bandwidth to track all these entities. Similar goes with the classes, which is for the like land, water, and its background. And haze, similarly, haze goes with the same thing, and with the snow to detect it with a different bandwidth. So we have this like these files. Now we are explaining the dataset directory. So I'm just continuing on this one. So here, as I have mentioned that we have tiles, and each tiles we have the different patches, and each patches we have the these 7 files, and these can be ranges from 1 to 25, and in each tiles you have patches which can be ranges from 1 to either 45 or 52, and these are the splits. In this the EG and hard, in this basically you have the path of the data.npy file. Okay, now going I explained this thing like converting hyperspectral TF image to NPY, and here we can start with the our main goal to analyze the files. Here is the like this is the directly which can, if we are using in your local system, then you can just need to change the path of the directory. This is what I have mentioned, that these are the invalid channels with different bandwidth which we do not require. So we have mentioned over here, and here we are converting it. Here you can see this is a test run to check whether that my file is getting converted or not. So if you see that it is getting converted over here, and now in going down here we have tried to check the total number of patches. This is pre-check. In this we have like 1222 overall patches which are present. That is basically the NPY file from each patch we have taken. Here we are just converting the patches, like converting that .tif file into .npy file. So here we are trying to convert in patches like not going all at once, but going to like after one patch, it will just hold, then again next. And here we have checked the file type of the TIF, which is int16 with dimension, height and width 224, 128, 128, which was mentioned earlier. And when we have converted this into .npr file, then it's converted into float32 with 202 channel, because we have removed uh, the invalid channels, and it remains the pic the height and width remains the same, which matches with the TIF. And now we are going for the model architecture. Like the model, you can access the model from cloning from here. In this, if you go, there is a folder name with model. You have all the models over there. From there, you can access the current model which we are using, that is SSCNet. So this is a model overview, and here you can see the model summary.
Can you please explain about why you picked up this model and why not others?
Yes, the reason behind for picking the SSCNet over other model is, like, since SSCNet achieve efficient compression through the fully convolution design, and when we are dealing with CAE model, 1D model, and we are trying to use faster AI, in that it was not compatible with it. So because of that, we have to switch to SSCNet.
Why they are not compatible?
Mm. They were not able to process the 1D convolution when we are trying to do that one. And the other reason also for selecting this over other is that the SSC net structure is computationally less intensive for specific tasks compared to CAE models. So this is the model summary we have, and going further ahead to visualize the data of the HySpecNet. So here we have some checks. Like first one is like mostly blank. We are checking that this function determines whether the majority of pixel is given in image are blank or zero. This is basically used to filter out the images that do not contain enough useful data for further processing. And then this function basically includes like collecting all the TIF files from the CSV. And this is used to enhance the contrast stretching. And here, if you go ahead, you can see these are the different bands. These are coming to be black because there is all the channels are maybe in the black category, and here because it is coming blank because here everything will be like either zero, mostly it will be zero, that's why it is coming over here. Then if we talk about we have done the test run, so here we need to set the parameters before running the test. The default one is here, like this you will get it from the repository. You will get the default one, that is you will have a batch size of 64, then the path, then you have the model CI1D. And before doing this, there there are pre-trained weights which are available. You can download it from the here from the link over here, and you need to place this one in your result wait folder. In this directory, you need to place this one to run the test set. So for the running test, you need to run few commands to like make it readable. So you will first check with the cat.test.sh that whether all the things are there. Then you just change the mode and then you execute the test.sh. So when you execute it here, then you will get wait.json file, which will be accessible in the test folder, test directory. And from there, you can see the results here. The results which we get is like the PSNR we are getting at 43.37 dB, which is good because all the PSNR which is above 30 is considered as a good PSNR. Then we have SSIM 0.97, then spectral angle 1.84, and then the other KPIs. Now, after doing this, we move ahead for the DNN compression pruning. So here we have just used the compression technique which we have done earlier in the compression file. Here we have used the pruning, and from here we have accessed the file which is generated from here in this. So if we evaluate the KPIs, which is first the peak signal to noise ratio, so it is coming out to be, for the original model it is 43.37, and for our quantized tune model it is 36.09. It is less than the actual one, but it is above the 30, so it can be considered as a good. And then we move ahead with the number of parameters. Then we have, in the original we have this parameter, and which is now get reduced to this. If we talk about the mean square error, in the original we have MSE loss is 0.00049, and here we have 0.00268, which can be considered as good. And for the spectral angle basically tells that your original image and your compressed image, how much they are either it is distorted or not. So we are getting like higher degree in quantized model, which is basically telling that it is not that much distorted, it is like more on a similar scale. And this is the SSIM, which is structural similarity index, which basically tells like how your current and your original model are structurally similar. So there is not that much difference we can see over here. So it's like all the parameters and everything are similar to the original ones. And this is the inference time, and we have the RAM use over here. This is used for the original one, and this is when we have compressed this one. And if you talk about the model size, so the original model size was 52.59 MB, and after compression, doing pruning, it reduced to 30.20 MB. So we can see that the compression percentage 42.58% we have achieved. If we talk about the bit per pixel per channel, So in the earlier.ti file, it has 16, and when you have converted it to our file .npy, we have 32. And moving ahead, we have got all the comparisons over here. So you can see that if you talk about the model size, we have a better one with the VRAM also, and also the spectral angle we have better, and the PS now relatively we have the on same. Okay. So this is the analysis which we have done on HySpecNet11k with the SSCNet on SSCNet model.
Yes, thank you. Then does Hiroshi stop recording?
Sure, just a moment.